Okay, so in this video, we are going to cover another GPU scan algorithm, algorithm, algorithm. This will be a more work efficient algorithm as opposed to what we saw the last time, the Kogge-Stone algorithm, which was not as work efficient. So let's start by talking about what work complexity actually means, right? If an algorithm is doing more work, that means it is performing more additions then required to get to the same result. So to get to the same result, we only need n operations, but we are doing n log n. So going to a more work efficient algorithm will just involve us to somehow reduce these number of operations. Just by looking at the computation for the Kogge-Stone algorithm, it's not intuitively clear to me what else we can do to reuse these partial sums, or what sort of reuse we can expose through this computation pattern. The first thing, let's start by replacing all these numbers by variables. So from x0 to x7, because it will be easier for us to track where a particular variable ends up in the computation pattern. Right. So now we have the same computation written down with variables instead of numbers. So now let's look at the evolution of x2 and x3 in particular. It goes from being x2 to the sum of x1 plus x2 to the sum of x0 plus x1 plus x2. It starts from x3, it becomes x2 plus x3, and in the next level it becomes the sum from x0 to x3. The important thing to note here is none of the work we did for x2 or the evolution at position 2 was directly reusable for the evolution of position 3, right? Even though their final answers have like 3 of the 4 same elements, all of them consist of x0, x1, x2. So if you're summing all these numbers, you would want to reuse the sums as much as possible. But in Kogge-Stone, we see no reuse between these adjacent positions. So now let's contrast this with the evolution of positions 2 and 3 in the serial algorithm. So what happens in the serial algorithm is initially you have x2 on position 2, and once the algorithm runs, you get the sum from x0 to x2, which is the final answer. Then for the third position, you have x3 at the start, and then it reuses the entire sum from x0 to x2 from the previous step and then just adds x3 to it. So there's just one extra addition, and it basically reused the entire result of the previous computation. Now let's begin thinking about how we can make or how we can structure the computation in a way such that we can expose more of these partial sum reuses. We want to compute the reduction of a subarray starting at 0 and ending at the current position. So for every element, we start the subarray at 0 and end it at the current position, and we want to compute the reduction of that, and that value will be the scan result. The other thing we know is that a reduction tree is the most work efficient way to compute a reduction. So let's just start by doing a reduction tree on the entire array, because we know that this will at least give us the result of the final element. So in this output, we see that we not only get the result for the final element like we expected, which is the sum from x0 to x7, but we also got the result for the 0th position, which is trivial, but the result for the first position and the result for the third position. So we expected the result of the final element, but we got 3x extra for free, basically. Not bad, right? By now, we have only done one reduction tree on n elements. We have basically done n minus 1 operations. So our work efficiency is still linear. It hasn't gone into the superlinear domain yet. But now what do we do? This is not the result we want. How do we go from here to the actual scan result that we want? So let's talk about Brent-Kung first, right? Looking at this array, looking at this partial result that we got, how do we move from this to the actual result we want? So let's start by inspecting the array that we have in front of us and see what elements or what values each position needs to get to its scanned result. 0th position is done, x0 is the final result. First position is done because x0 plus x1 is the final result. The second position is not done. We are still at x2 there, but we want to go to the sum from x0 to x2 somehow. So the second position is not done. The third position is done. It is the sum from x0 to x3. The fourth position is not done. The fifth position is not done. The sixth position is not done. And the seventh position is obviously done. So we still have incomplete results for 2, 4, 5, and 6. How do we complete those? For position 2, we have the sum from x0 to x1. For position 4 and 5, we have the sum from x0 to x3. And for position 6, we don't have the sum from x0 to x5 directly, but we can see a way of getting there, right? That is, we can just combine the sums from x0 to x3 and x4 to x5 to get the sums from x0 to x5, and then just take that sum and add it to x6. Now that we have determined that there are some incomplete values in our result, and we have the values that would complete them, all we need to do now is to just add these partial results to the positions that need them. But how do we go about doing that? How do we organize this computation? Okay, so let's separate out the computations we need to do by the distance between the partial results and the position that needs them. Now, what do we do? How do we do these operations? We'll just execute them in a tree-like fashion, where all the additions between the values that were the fixed distance apart will happen on the same level. Now let's talk about the work complexity of this algorithm. So we started with a reduction tree, and that was just one reduction tree for over the entire array of n elements. So we did n minus 1 operations, so that was just linear. But what about the downward pass? So we had one addition in the first pass of the downward phase. We had 3 additions in the second pass of the downward phase. And if we continue this pattern, we get then 7 additions, then 15 additions. And the pattern that emerges out of this is basically 2 raised to the power r minus 1. So if we just sum this series over log n base 2 minus 1 levels, we'll get n minus 1 minus log n base 2 number of additions, which is still linear. So the upward pass, which was just a reduction tree, was linear. The downward pass is linear. That makes the entire algorithm linear, as opposed to the n log n work complexity of Kogge-Stone. By the way, there is another cool way to look at this analysis. So just imagine a binary tree where every node is the sum of its children and the leaf nodes are just the elements in the array. There will be exactly n minus 1 internal, that is non-leaf nodes in this binary tree. And the first branch, right? So from the root to the left of that root, to the left of that root, to the left of that root, all the way down to the leaf node, will be the only branch of the tree which will not need any corrections to its prefix sum, right? Because it starts at x0. And what is the depth of that binary tree? That is just log n base 2. And that is exactly what we subtract from n minus 1. So the total number of additions we need is just n minus 1, all the internal nodes in the binary tree, minus log n base 2, which is the height of the leftmost branch. But yeah, we got our work complexity and it's linear. So this is officially the most work efficient parallel scan algorithm we have seen so far.